Hello and welcome to the third discussion of the fluid mechanics. Okay, so previously we have talked about the property density and a little bit about the viscosity, the mechanisms by which the viscosity plays the role of message propagation in gases and fluids. Sorry, in gases and liquids, right? Okay. So now let us take up the mathematical formulation of the concept of viscosity. Okay. So uh, firstly, so the heading will be like, let me first put the heading. Okay. Sorry. So the heading is viscosity continued. Okay. Viscosity continued. So in case of solid, uh, there is this stress strain relationship. Okay, stress strain relationship. Okay, but in case of fluids, so this is the for solids, this is very important. Okay, and based on this we have the Young's modulus, right, the Hooke's law, that is the E equal to stress by strain. Okay, but for fluids, in fluids we have the continuous deformation. I have shown that for the continuous deformation we need a negligible amount of force or stress, right? So by that negligible amount of stress, we can have a continuous state deformation. So the deformation is there for a longer period of time. Okay, and therefore in fluid, not the deformation but the rate of deformation. Okay, rate of deformation, because I mean rate of deformation is important, because in solid we can have the situation, like, if we put out the load, if we put off the load, then the deformation actually stops. So there we are having the concept of the deformation and therefore the strain. But here the rate of deformation and thusly the rate of strain. Okay, the rate of strain is what we are looking for. Okay, is what we are looking for. So what is this rate of strain? Okay, so uh, first let us say that the for the shear case. Okay, so if we consider the shear deformation of this block, okay, so then we can have it like this. So this angle, right, is alpha. Okay, so let us say that this is, okay, this is delta x and this is that's h. So this tan alpha equals to, this tan alpha equals to what, this by this. Okay, and this is nothing but the shear strain gamma. Okay, shear strain, right? So therefore this rate of strain will be now shear strain or unit time, right? And that is equals to del x by t, lt actually, h, and that is nothing but x dot by h, right? So this is the shear strain rate. So this is the strain rate, okay, and this is nothing but the velocity by height here, okay. So this is the velocity by height, and in differential form, if the stress or if the this velocity is a constant function of the height, then at different heights we will get a different value of the velocity gradient. So in differential form, it is equivalent to dv, okay, dv by dh in differential form, okay. So the I think so these are the concepts of basic calculus actually, okay. Okay, so this is not equal, but this is equivalent, okay, equivalent, okay. So that is dvdh, the velocity gradient, okay, fine. So I have shown you the case of two parallel plates, right? I have shown you the case of two parallel plates and having a fluid in between, right? Okay, so now let us consider this axis, okay, and also this axis, okay. So this is x and this is y, fine. And the situation is that this plate is having v equal to 0, and this plate is having v equal to, let us say, something v, small v, okay, velocity equal to small v, and this plate is pulled by a force capital F, fine, okay. So this is a shear force on the plate, and therefore the shear stress will be tau equals to F by the area of the plate. Area means, if we consider the plate like this, then this is the A, right? So this is the concept of shear stress, so, we all know, right? Okay, now let me just put this arrow here, okay, okay. So and we have shown that because of viscosity we have a velocity profile something like this. I have told that I am not ensuring the shape or the profile of this velocity profile up till now, but it will vary from 0 to v here, okay, but this variation is we are not sure about this, okay. Now in fluid mechanics in the governing equations we have this force, okay. I mean, I will derive all those governing equations, the Navier-Stokes equation, and in those equation, what we have to do is we have to write this equation, F equals to ma, and this is nothing but the summation of external forces, and this is just mass time acceleration. So during this summation of external force derivation, we will have this shear force, this shear force, okay, this shear force, and therefore in this equation this tau term will be there, okay. But we don't need the governing so we don't need the governing equations in terms of the tau, and we only need the governing equations in terms of some very important parameters for fluid mechanics, and they are the uh, pressure, density, velocity, right, and the space coordinates and time. Okay, so these are the parameters in terms of which we need the governing equation. Okay, therefore we must need an equation that will relate these two things. Okay, that will relate these two things. So that relationship or that equation is having a particular name that I will tell you later during the derivation of the Navier-Stokes equation. But up till now, okay, up till now, it can be shown only from the experimental studies, that is, at least for some fluids, this tau is proportional to this rate of strain. Okay, this rate of strain. So this du dy is what? At any point, if I draw a tangent, so this tangent is representing the du dy, the slope, right? The angle made with the uh, horizontal, right? Okay. So believe me that I have told that this is the F, and thusly this is the shear force on the plate. So why this shear force is coming? Because there is an opposing force, right? There is an opposing force on the fluid layers. Okay, and actually the individual fluid layers here. So if this is a fluid layer, if this is a fluid layer, this is a fluid layer. So this fluid layer, because of viscosity, will have a pull in this direction, but with a lesser velocity, and this also will have a pull. Okay, so and why this plate is having a pull with a lesser velocity? Because this plate, this layer of fluid is having an opposite pull. Okay, is having an opposite pull, is having an opposite pull by this layer. Okay, by this layer. Okay, and this pull is nothing but a force. So not only this plate, but every layer in this fluid is subjected to a particular shear force. Not only shear force but also a normal force, but here this in this analysis we are only considering the shear force. Okay, so each and every layer of the fluid, okay, is subjected to a shear force. So at each and every, okay, just let me remove this fluid layers, okay, and these things. Okay, okay, so at every point, sorry, so along y, at every point I will have a particular amount of shear force. So shear force at a distance y, okay, so let us say at a distance y equal to h, is proportional to the velocity gradient at a distance y equal to h. What I am saying, that let us say that this distance is h. Okay, so shear stress at this point is proportional to this tangent, this tan theta. Okay, so tau at h is proportional to this tan theta, that is du dy at h. Okay. uh, in appropriate mathematical form, I should replace this by, I should replace this by del u del y, because u can be the function of both x and y. So that's why I should write the partial derivative and not the ordinary derivative. Okay. So now if I put a constant, okay, that is tau equals to mu du dy. Okay, I am not writing this h and h again and again. Just assume that it happens for any h at any height. Okay. Okay, so this thing only, okay, is known as, okay, is known as Newton's law of viscosity. Okay, Newton's law of viscosity, and this mu is known as coefficient of viscosity. Okay, coefficient of viscosity. Fine. Okay, so and this is directly the representative of viscosity. Of viscosity. That means that means if we have to tell someone the viscosity of any fluid, we just tell this value of mu or the value of another thing that I will describe just now. Okay, so this is the coefficient of viscosity. Okay, so now units of mu. Just I don't have memorized the I don't have memorized uh, the actual unit. I always do it by dimensional analysis. So mu equals to tau into dy by du, and tau is equals to Newton per meter square, force per area. So Newton is equal to mlt to the power minus 2 by meter square into meter by time, right? So this is here and this is this, so m l minus 1 t to the power minus 1. I think this is coming. Okay. Okay, so in SI this should be kg per meter second. Okay, now if I multiply some acceleration into this, that is meter per second square up and by meter per second square down, then this will be some force. Okay, force, because this mass into acceleration is force, that is Newton. Okay, by this m and this m, so by meter square. Okay, and so this m and this m is meter square, and here is a s into 1 by s square, right? So this is Newton second per meter square. So this is nothing but Pascal second. If so if you think that I have done it a bit faster, then just arrive it by yourself. So this unit is also used rigorously. Okay, is also used rigorously. Okay, now I will tell you about a very important concept of kinematic viscosity. Okay, kinematic viscosity. Okay, that is kinematic viscosity. Okay, so one thing you should note here, that is this shear stress. So this is also something called viscous shear stress. So it may be imperative that for all the fluid in all the situation there should be a viscous shear stress because of because we don't have any fluid with zero viscosity. But if in any situation this du dy becomes zero, then this viscous shear stress is also zero, and that does not mean that the viscosity of the fluid is zero. Okay, so just listen very carefully. Viscous shear stress can be zero, but viscosity cannot be zero. Okay, now let us come to kinematic viscosity. So it is denoted by the letter nu. So nu equals to mu by rho. Okay, so viscosity by density. Now we already have the uh, parameter called mu, this dynamic viscosity, which is also called dynamic viscosity. Okay, this dynamic viscosity, dynamic viscosity. So uh, again, uh, why do we have this kinematic viscosity? Okay, so here you can see that I have told the variation of viscosity with temperature, and it has a significant variation. Okay, but actually you can see here by your intuition only, that is if let us say for gases. Okay, if I increase the temperature. Okay, if I increase the temperature, okay, then the viscosity actually increases and the density also increases intuitively. Okay, I am saying again and again, that is intuitively. Okay, and for liquids, as we increase the temperature, the viscosity decreases and the temperature increases. Okay, so at least for gases we can say that as the mu is increasing, the rho is also increasing. So somewhat the temperature dependence of this kinematic viscosity is very less than this dynamic viscosity, and for that reason this is a more suitable property to be mentioned, because if you mention the dynamic viscosity at a particular temperature, then at another temperature it may vary, then your customer can complain. But so this will be a bit safer option to be mentioned. Okay, but for the fluid it is, I mean sorry, for the liquid it is showing something opposite, that is if we increase the temperature, then the mu is decreasing and rho is increasing, and therefore nu should also decrease. Okay, so so this logic is not always true, this logic is not always true. But from the fluid mechanics point of view, from the fluid kinematics or dynamics point of view, this parameter has a greater uh, implication. Okay, and now what is that implication? So mu is representing what? It is opposing the motion. I have told you, right? Opposing the motion. Okay, and rho is what? Representative of, representative of mass, right? And now we all have learned about the inertia, and mass is the measure of inertia, right? So mode is the inertia, more will be the tendency uh, to be in the motion in which the particle is currently at, right? So if the particle is moving, then this rho then this rho will help in motion, right? This rho will help in motion, because more is the rho, more is the mass, and if the particle is moving, then the motional inertia will be more, so it will help in motion. That is, if we have a larger football, okay, and if we have a smaller ball, okay, and both are rolling, okay, and both are rolling, to stop, we need a greater force for the larger football, and and obviously I am talking about neglecting friction. Okay, neglecting friction. If if on a frictionless force, if on a uh, frictionless floor, both the large ball and the small ball is rolling, then to stop the large ball, we will require a larger amount of force, right? So that is the effect of inertia. So being large, it has the larger mass, and therefore the so this mass will help in the motion. Okay, so this rho is opposing, so this rho is supporting the motion, and this mu is opposing the motion. Okay, so whether the fluid so whether a particular fluid will have the tendency to move between a constriction, okay, that will be dependent not only by mu but also by rho. And so this combined effect is very important, and that is dictated by this kinematic viscosity. That is dictated by this kinematic viscosity. Okay, so in other words, so just grasp this all point of views. Okay, if we have again this kind of two parallel plates and a fluid in between. Okay, so then this plate is, let us say, fixed. This plate is fixed and this is moving. Okay, okay, so this fluid, by coming from here with an uniform velocity, is understanding that yes, here I have a plate that is stationary, and here I have a plate that is moving by the velocity v. So these two messages are being propagated to the fluid by the viscosity, but this message propagation can be disrupted by the density. Okay, if the density is very high, then the inertia is very high, then the flow of the fluid will suppress this message propagation. Okay, and these all things are actually can be shown in the boundary layer theory. Okay, and the implications of Reynolds number. Okay, in that case I will show you this the significance of kinematic viscosity uh, in a very good manner. Okay, okay, so by similarly performing the dimensional analysis, we can find the, okay, we can find the units and the dimension of this kinematic viscosity. Okay, okay, so here just I will take up a note. Okay, just note down, note down carefully the relation between Stokes, okay, poise, centi-Stokes. Okay, okay, so these things just do it by yourself, okay, because these are just the facts, okay. And why these are important? Because in examination you can be given the value of mu in Stokes, okay, or in Poise, okay. So then you should be able to understand then that how to convert it to the Pascal second to solve the problems, okay. So these are the defined units easily available in the internet, okay. I am not wasting time in these things, there is nothing to understand more, okay. Now now I have shown that for fluid this relationship between, okay, so relationship between tau and this velocity gradient, the shear strain rate. This is very important, okay, this is very very important, okay. And now, so there is, so now if I plot, if I plot this thing, okay, now if I plot this thing here tau and here du dy, I have said that for some of the fluids only tau is proportional to du dy, and for that case only we will be having what, a straight line passing through origin, right. So this is the case of tau, uh, just let me write it clearly, tau equals to mu into du dy, okay. But another cases are there, okay, based on this relationship. So first of all, here the relation between the shear stress and the strain rate is linear, but we can have some non-linear relationships and having the equations like this, okay, like this. So in this case we can have two types of curves. One is like this, nothing. One is like this and another is like this, okay, okay. And that will directly depend upon the value of n, okay, the value of n. So now just look at this yellow curve, and what is happening in this yellow curve, the slope, the slope here is this, at this point the slope is this, the at this point the slope is this, at this point the slope is this, and at this point the slope is this, okay. So the slope is increasing, and what is the slope, this theta. So this theta is increasing, so the slope is increasing, okay. So the slope is increasing, okay, okay. So if the slope is increasing, and what does the slope actually means, okay. So now, so what does the slope mean? From this formula we can modify this as, right, by this. Now if I tell this as mu apparent or the mu effective, so then I can write it as mu apparent into du dy. So at any du dy, at any du dy, if I am taking the slope, then it is nothing but the, so slope is nothing but the, this tan theta is equals to the mu apparent, right. This tan theta is equals to mu apparent directly from this equation, right? Directly from this equation. Okay, so slope is mu apparent. Okay, this mu apparent or mu effective, whatever you call this, so this mu apparent is nothing but the representative of the viscosity at that particular strain rate. Okay, at that, so at this strain rate, so this is the viscosity of the fluid. Okay, so this is the implication of mu apparent. So for this yellow curve, what we are seeing, that as we are increasing the strain rate, the mu apparent is, the slope is increasing, and thusly the mu apparent is increasing. So as we are increasing the strain rate, then the mu apparent is increasing, and the fluid is becoming more and more viscous. So it is like the quicksand, very dangerous quicksand. So in the quicksand, as he was trying to move more and more, then the quicksand become more and more viscous, and therefore your movement becomes more and more restricted, right? Okay, so, and just observe that as I am increasing the shear strain, the viscosity is increasing, so the shear stress will also get increasing, right? So therefore this is called shear thickening. The value of shear stress is being thickened. Okay, shear thickening, shear thickening fluid, shear thickening fluid. Another name is dilatant fluid. Okay, now if someone uh, gives you the curve and just asks you that what is the type of fluid, you don't have to memorize. You have to just see the change in slope. If the slope is increasing, then it is the shear thickening fluid. Yes, the other name you have to memorize, but the cause of the naming of shear thickening is, I guess, clear, right? If not clear, please comment. Okay, now let us come to the pink colored curve. So this is the slope at this point, this is the slope at this point, this is the slope at this point, and this is the slope at this point. So here the theta is this, here this, here this, and here is this. So here the slope is decreasing, and thusly the mu apparent will decrease, and because of that reason this pink curve is known as shear thinning. Okay, shear thinning fluid, or another name is pseudoplastic. Pseudoplastic. So the example is blood. Okay, example is blood. Okay, okay, so this is very important, and now these things are not have ended here. Actually, there are other types of fluids also. So uh, what are those other types of fluids? Now let me draw a line right here. Okay, let me take some different coordinate axes. Okay, okay, let them be there, and let me take some different coordinate axis here. Okay, so again I can draw three lines, and one is this, another is this, another is Let us say, let me, okay, let me draw by blue. Okay, another is this. Okay, so the same types of graphs, but here they are not passing through origin, right? So now uh, the equation can be mu du dy whole to the power n, but having some intercept. Let us say that this is tau naught. Okay, that this is tau naught. Okay, so this will be the equations, here tau and here du dy, the strain rate. Okay, so here this tau naught is nothing but the like the yield strength for the solid cases. And what is the yield strength? That is, before that strain, the solid is not beginning its plastic deformation. Okay, alike that, alike that. Okay, this tau naught is the amount of shear stress above, uh, under under which the fluid will not show any deformation, any strain rate. Okay, the strain rate is 0. Okay, okay, so I think the implication of tau naught is clear to you. So this curve is something called a Bingham plastic. Okay, Bingham plastic, and this is known as thixotropic. Okay, and this is known as rheotropic. Okay, so I don't have anything to memorize this, because these are just names. You have to memorize this. Okay, okay, but so these were the types of fluids based on the relation of this stress and strain rate. Okay, now there can be a general equation for any fluid. Okay, so we can't say that all the fluids of the world will come under these 6 categories. Okay, a fluid can have its own shear stress and strain rate diagram. Okay, and can have a equation like this. So this equation is widely known as power law fluids. Okay, power law fluids equation, power law fluid equation. Okay, okay, so there are also other types of laws or equations. Okay, in this equation, this is flow consistency index, and this is flow behavior index. Okay, 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 so this is the end of viscosity. Okay, so with viscosity we have covered a lot. Okay, we have covered a lot. Now let us come to a very important property called surface tension, right? A very important property called surface tension. Okay, okay, so now let me take some example. Okay, I have I have told you about the intermolecular forces of attraction, that is the cohesive forces. And if the forces are between the dissimilar molecules, then that is the adhesive force, right? Okay. So now just think of some phenomena. Okay, that is when the um, raindrops fall to the ground, then they generally acquire the spherical shape. Unlike most of the fluids that we see in our daily life, the mercury droplets can roll on any surface just like a ball, right? Some some creatures, like some insects, can jump and walk on the river or the water. So these are some phenomenal examples. So I am taking here the example of an insect. Okay. So let me consider this as the surface of a river or a water, and I am having an insect here. Okay. So this is an insect. Now this insect has its own mg weight. So there must be some force that is giving an upward force, by virtue of which the insect is able to be on the water, right? Now we have to find that what is that force. Okay. Okay. I am giving you some intuitive approach here, if you don't have till now. That is because of the weight, because of the weight of this insect, just like a membrane, the water surface will be like this. Okay. Now we have something like this force F, and here also F. This upward component of this force F is actually balancing, and these downward components are being cancelled. Okay. So there can be something like this. Okay. Okay. There can be something like this concept. Now let us come to the origin of the surface tension. Okay. So just consider a tank and water tank. Okay. Just consider an water tank. Okay, just consider an water tank, and this is the water level. Okay, this is the water level. Okay. Okay. So now consider two molecules in the tank. Okay, one molecule is here, another is somewhat uh, here. So consider this molecule A and this B. Now for this molecule B, I have different molecules surrounding it, right? Different same type of molecules. So here will be a cohesive force, here will be a cohesive force, and directly opposite to this line I have another molecule having the same amount of cohesive force cancelling this one. And for any of these cohesive forces, I have any of these opposing molecules cancelling all the forces. So for this molecule, net force on this molecule is 0, right? But for this A molecule, I have one molecule like this surrounding here, 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 and here. But in above, I don't have the water molecule, I have the air molecules, right? I have the air molecules. So this cohesive force, sorry, this cohesive force and this cohesive force are not equal. So net force here is not zero, okay, because this is not actually a cohesive force, this is a adhesive force, okay, this is an adhesive force, the force between the air molecule and the water molecule. And sorry, and the adhesive force or the air air water molecule force, this attraction force is far less than the water, okay, water, okay. So knowing this fact, this molecule here will experience a negative pull, right, will experience a negative pull, okay. And because of that, all these molecules here will be tend to be compressed, will be tend to be compressed. So another force apart from the cohesive force, that is a force opposing of this compression, will go in upwards, will go in upwards, okay, will go in upwards, right. So therefore I am exaggerating this surface, okay, sorry, I am exaggerating this surface here, and so this is the air and water interface, and here are the molecules that are at contact with air, and here are the just vicinity molecules, okay. So these molecules are having a net downward pull, so they are having a tendency to have a net downward motion. To oppose that motion, all these molecules should give a net upward force also, right. And by this phenomena only, this surface can be maintained, this surface or this orientation can be maintained, okay. So the force that is required to maintain of the orientation of this fluid interface surface or the fluid solid also, that I will take up in the next discussion, but now only this fluid 1 and this is fluid 2. So because of this adhesive force only, the surface tension has been generated, and therefore to maintain this fluid or I should say fluid 1 fluid 2 interface orientation, to maintain that I need the surface tension force, okay. So if I take the uh, top view, okay, this top view of the surface, okay, just let me draw it clearly, that is I am saying that if I take this top view, this is the fluid layer, and if I take the top view, I will see something like a square if the base of the tank is square, right. So this is the fluid surface, okay, and the surface tension is acting at each and every point of this surface, okay. And if I take a string, let us say if I take a string here, if I take a string here, okay, then then the surface tension force will act on the surface like this, to maintain each and every point of the surface in equilibrium, it will act like this along a line, okay. And therefore the surface tension is actually defined by, okay, uh, I am taking the symbol of, let us say, T. Okay, there are various symbols. Okay, okay, so I can take as temperature this T, but so let me take this as sigma s. Okay, sigma s is defined by this force of surface tension by the any length taken across any direction. Okay, taken across any direction of a surface. Obviously, uh, if the fluid is not isotropic, that is the directional dependence can be there of any property, then surface tension can vary the uh, with the direction also theoretically, but in practical those cases are not there. Okay, so this is the mathematical definition of surface tension. Okay, this F by L. Okay, now again the question actually comes that why this is happening, that the that raindrop is having a spherical shape only. Okay, or why the mercury is having a spherical shape on any solid surface as well. Okay, so to answer this question, let us perform some experiment. Okay, so let us take a frame like this, and the frame, these three sides are fixed. Okay, these three sides are fixed. Okay, and this side is movable. Okay, and here is a fluid. I have a fluid here. Okay, I have a fluid here. Okay, so in this experiment, you can see that after, so I am applying some force to this frame. Okay, force to this frame. So, and this force is very little and is increased gradually. Increased gradually. I have told that the surface tension is all about maintaining the orientation of the surface. Now, you will find that after a particular time, the plate is this this link is moving uh, to this position, and after a particular time, this liquid, this surface will break. This surface will break. That means the surface tension is not working. That means the surface tension is not working anymore, because if the surface tension has been working for this uh, for this surface only, then after expanding also, this surface should have been there, but after a particular amount of delta x, okay, the this surface will break into the liquid drops or the liquid droplets. Okay, that means this extension towards this is in the favorable direction of the surface tension. Okay, surface tension does not want to be increased, uh, to be, or rather I should say that the direction of surface tension on this plate is not here, it is in this direction. Okay, it is in this direction. So this is the surface tension force Fs. Okay, and also we are seeing that after a particular increment of delta x, this surface is breaking down. Okay, this surface is breaking down. That means surface tension does not want this increment in x. More is the increment, the surface is being weaker and weaker. Okay, so that means the increment in x means increment is, so this is L. Okay, so increment in delta x means increment in surface area, and that directly means that surface tension does not want increment in surface area. Okay, that means surface tension always tries to minimize the surface area. We can know by this simple experiment. Okay, this is just an experiment. So surface tension is always trying to minimize this area. Okay, now, so if now this is the case, that from this experiment, so this is the statement that surface tension always tries to minimize surface area of fluid fluid interface. Okay, fluid interface. So this is a very important statement. Okay, this is a very important statement. Now I will show this thing by mathematically. Okay, so I can see that the surface tension is acting like this. So it is acting like a rubber band. So if I fix a rubber band like this, if I fix a rubber band here like this, then also if I apply some force F, then the elastic potential energy of this rubber band will increase, and the tension will be at this direction. Though, so the surface tension is also acting like that only. So that means by just analogy, as so if I could, okay, let me just do a bit more clarity. So just let me take the similar system uh, once again, and I am just quickly draw it. I will. So uh, okay, so in this situation I have this elastic band. Okay, I have this elastic band and not the fluid. Okay, and I am again applying the same force F here. Okay, so then I will have a tension force T here. So this T is analogous, not equal, I am saying, to this Fs. So as I am applying this force F, then the potential energy potential energy is increasing. Okay, now this is for the T case, for the rubber band case, and for the surface tension case, as I'm applying the F, as there is a similar effect, so there is something, the same kind of potential energy should be there. Okay, and now here the surface itself is replacing the rubber band, so the surface energy, that is also a type of potential energy, is increasing. This surface energy is increasing. Okay, this surface energy is increasing, and we all know that whenever, and the same case, if you are constantly pulling this, so then after a particular time this link will come to this position, and this rubber band will break. So as we are making this increment del x, then the potential energy is gradually increasing and increasing, and this increasing in potential energy is is subsequently making the rubber band to break. And similarly, as we are in this case, as we are increasing this del x, this surface energy is increasing and increasing and increasing, and therefore the surface actually breaks like that rubber band only. So to minimize the surface area will be the only objective of surface tension. Okay, and in nature sphere is having the minimal area. That's why the raindrop is having a spherical shape. Okay, and why the mercury is having the spherical shape not only in the air but also in the solid surface, that you can try to think, and I will explain it in the next discussion, because it is uh, it is so much related to the capillarity effect. Okay, now just let me mathematically define the surface energy concept. Okay, so just uh, take up this situation. Okay, this situation here, and just remove this one. I will do some mathematical calculation. So let this is the dx, the elemental um, increment in the length by pulling. So for this change in elemental length, so after every elemental incrementation, we are allowing the system to be in equilibrium. So this F will always be equal to the surface tension. Okay, okay. Now, so therefore, the work done is nothing but this. Okay, this is the work done, and by the work energy theorem, okay, this work done will be stored as surface energy. Okay, as we stretch a rubber band, so that work done is stored in the as the elastic potential energy in the rubber band, same concept. Okay, now this fx into, so just multiply and divide by l. L is length. Okay, L is length. So L into dx is the incremental area, that is dA, right? So this is by L. So this is the surface energy. Okay, E surface, right? And now, so this is nothing but the, so this Fs by L is nothing but the surface tension. So this is this. So after the increment of dA, sigma, so after the increment of area of dA, the stored surface energy is surface tension into dA. That means surface tension is nothing but surface energy stored by the area of the surface. This is also a very important concept. Okay, this is also a very important concept. Okay, so these are the two implications of surface tension. One is one is this Fs by L is equals to Es by A. Okay, these are the two very important implications of the surface tension. You can think just this kind of problems, I think you have encountered for your JEE preparation. That is, we have a single droplet like this, having a particular diameter d, and this has been broken down into small droplets, okay, of n number having diameter d. Okay, so if this n is given, this d is given, then uh, okay, no, so this n is not given and this d is not given, only the surface tension is given. Okay, so then uh, what will be the uh, is number n. Okay, so How can you uh, proceed this? Just by equating the surface energy. Okay, so this is 4 pi d square by 4, or this pi d square, because this is the surface area of a square. Okay, 4 pi r square. Okay, into the surface area. And now, as this is the fluid property, it is, so this is equal to is into uh, 4 pi d square by 4, again d square by 4. Okay, so by this only. Okay, and also by mass conservation we can do this. Okay, so these types of problem actually we can do, or rather I can say that um, what can be the surface tension value up to which we can expand this bubble. Okay, so this also, there is a particular surface tension value up to, sorry, there is a particular diameter value d dash. Okay, so as we are increasing, so the change in surface energy will be something pi d square. Okay, that is pi into d dash square minus d square into surface tension. Okay, so these are the change in surface energy. Okay, so these are the concepts. Okay, this problem you can visit again. This is a very simple problem actually. Okay, so I will take up the capillarity effect in the next discussion. So until then, bye and take care, and don't forget to put your suggestion and comments on the discussion. Okay, on the comment box, that if I have to improve something, just remember that I don't have uh, to say about any problem, because I have uh, just given an example of this problem. I have I haven't said that is about the official problem, so don't think it will be so you can get some similar problems from the PYQs. Okay, from the gate PYQs also I will take up some of very good example problems from each and every topic for gate purpose. Okay, so this was just an example. Just uh, just go through these concepts very well. If in any interview, if anyone asks you that how the surface tension force arises, you have to you have to talk about this adhesive force only. Okay, you have to talk about this adhesive force and tell the interviewer the whole story. So in the next discussion I will take up the case of mercury and the capillarity effect. Until then, bye bye, and just take care. Thank you.